So this is question 9 from the sample assessment materials. This is a ladder problem, so we're probably going to end up taking moments at some point. So we've got a uniform ladder AB of length 2A. So that means that, and it's weight W. So that means that that weight is in the middle there. We'll come to that on our diagram in a minute. It's got its end A on rough horizontal ground. The coefficient of friction between the ladder and the ground is 1/4. The end B is against a smooth vertical wall. A builder of weight 7W stands at the top of the ladder. To stop the ladder from slipping, the builder's assistant applies a horizontal force of magnitude P to the ladder towards the wall, and it acts in a perpendicular direction, so it's going there. Again, we'll add that onto a nice big diagram in a minute. The ladder rests in equilibrium in the vertical plane. So that just means it's not sort of tipping away from us in our diagram or tipping towards us. And it's modelled as a uniform rod. Tan alpha is equal to 5/2 as well. So that's going to come in handy later. Part A wants us to show that the reaction of the wall on the ladder at B has magnitude 3W. So let's start by drawing a nice big diagram. So I've got my ladder, my vertical smooth wall, my rough horizontal ground. It's 2A long and it's got weight W, which is acting there in the middle. It's at angle alpha. Their builder of weight 7W is at the top of the ladder. And the builder's assistant is providing this horizontal force P to hold the ladder in place and stop it slipping. Now, the other forces that are in play here are our reaction forces. So up here at B, there is a reaction force coming out in that direction. So the ladder is pushing into the wall is pushing back in that horizontal direction. And down at A, there's also this normal reaction here. So I'm going to call those R1 and R2. Now, it said in the question that we're trying to show the reaction force at B has magnitude 3W. So we're going to take moments about A. So that's using A as a pivot point, and it's saying that all of the clockwise forces at play are equal to the anti-clockwise forces. The ones that are pulling it clockwise are equal to the ones pulling it anti-clockwise. And moments are, to take a moment, you take the distance away from the pivot point and you multiply it by the perpendicular force. So we need to split these forces up into their parallel and perpendicular components. I'm not going to bother splitting these ones up into parallel and perpendicular components because they're 0 distance away from my pivot point. So they'll just be multiplied by 0 in the end anyway. So this one here has its perpendicular and parallel components. This bit is W cos alpha, because if that's alpha, that angle there is also alpha, and W sine alpha. Up here, the 7W again, if we've got one perpendicular like that and one parallel like that. So alpha in there, we've got 7W cos alpha and 7W sine alpha. And then the R1, we've got the perpendicular and the parallel. This angle here would be alpha. So this one is R1 sine alpha and R1 cos alpha. So now I'm ready to take moments. So because it's in equilibrium, we know that the clockwise forces are equal to the anti-clockwise ones. So clockwise, I've got this one here and this one here. So they're pulling it round in a clockwise direction. And in anti-clockwise direction, I've got this one up here. That's the one pulling it round in that direction. So we take the distance away from the pivot point and multiply it by the perpendicular force. So here, if this one is halfway up the ladder, it's A distance away. So it's A times W cos alpha. And we've also got 2A times 7W cos alpha. And then in the anti-clockwise direction, we've got 2A times R1 sine alpha. So I'm trying to show that the magnitude of the reaction force at B is 3W. So that's my R1. So I need to rearrange this to find R1. So I'm going to start by factorising over here. So I get A cos alpha out at the front. So for W plus 14W in the brackets. And 2A R1 sine alpha over here. The A's actually cancel. So I get cos alpha, and that's 15W, is equal to 2R1 sine alpha. Now in the question, they told me that tan alpha was equal to 5 over 2. So if I divide by cos alpha here, I can use that really easily. So 15W is equal to 2R1 sine alpha over cos alpha. So that's 15W equals 2R1, and then that's tan alpha there. So that's 5 over 2. The 2's cancel nicely. So I've got 15W equals 5R1. And if I divide by 5, 3W equals R1. And that's exactly what they wanted me to show in the question. So part B wants us to find in terms of W the range of the possible values for P which the ladder remains in equilibrium. So P is that horizontal force that the builder's assistant is putting in here, okay? So we're going to need to think about friction on this one. So friction could either be acting in this direction, or it could be acting in this direction. It all depends on how hard this builder is pushing here. So if they're pushing really, really hard, then the friction is going to be acting in this direction against them. And if they're not pushing very hard at all, then the friction will be helping them out, helping keep the ladder in place. So if we start off by thinking friction is going to be mu r, because it's at its maximum. So we're going to need R, and by R, I mean R2 here. It's going to be the normal reaction at this point. So let's start off by finding that. So if we resolve vertically, up equals down, because it's an equilibrium, R2 is equal to W plus 7W. So R2 is equal to 8W. That's going to be very useful. So friction is at its maximum, so it's equal to mu r. So mu in the question was 1/4, and r is 8W. So friction is 2W. So going back up to my diagram, it's either going to be 2W in that direction or it's going to be 2W in that direction. So if I now think horizontally, this one up here, we found this in part 1 of our question. This was 3W. So either this and this are going to equal P. So this 3W and this 2W going in this direction are going to equal P. Or this is going to equal this 2W and this. It depends which way friction's going. So either that way is going to be, I'm just working the horizontal plane there. It's going to be 3W plus 2W, which is 5W is equal to P. Or it's going to be 3W take away 2W, so W equals P. So the range of values for which P, the range of possible values for which P could keep it in equilibrium is going to be between W and 5W. Now, part C of the question says, often in practice, the builder's assistant will simply stand on the bottom of the ladder. Explain briefly how this helps stop the ladder from slipping. So let's go back to our diagram. So often in practice, our builder's assistant will stand here and the force will go downwards. Okay. So if they add more weight, that will increase this reaction force because they are directly proportional, aren't they? And then because friction is mu times this reaction force, it will therefore increase the frictional force. So let's write a sentence to say that. So adding more weight will increase R2 on our picture, which will increase the frictional force, which is mu R2 on ours. Hopefully I've put enough information in that one to get all the